One of the most peculiar things about physics is that sometimes the more carefully you look at nature, the less sense it makes at first. And the business of light is one of the best examples of this. Now, I'm going to tell you something that probably sounds absolutely crazy at first, and I want you to sit with it for a moment because it's not a trick or a paradox. It's just how things actually work. Light does not move. I know. You turn on a light and stuff gets illuminated. A photon leaves the sun and 8 minutes later we see it. So obviously light moves, right? But here's the thing. When we say light moves, we're using a description that's perfectly fine for everyday purposes, but when you get down to what's actually happening at the quantum level, what really happens in nature, light doesn't behave the way you might imagine it does. Let me tell you how we got confused about this in the first place. For a long time, people thought light was like a stream of tiny particles, little bullets coming from the sun. Newton thought that. Then later, people realized it behaves like waves, ripples in the water kind of thing. And for a while, this wave picture worked pretty well. You could explain reflection, refraction, all sorts of stuff. But then, and this is beautiful about science, we found out it wasn't quite right either. At the beginning of the 20th century, something strange happened. Experiments started showing that light sometimes behaves like a particle. Einstein discovered the photoelectric effect. You shine light on metal, and it kicks out electrons. And the energy of the electrons doesn't depend on how bright the light is. It depends on the color. That's strange. That's the behavior of particles, not waves. So what do we have? We have something that's both a particle and a wave. Or maybe it's something that's neither, and we're just using those words wrong. Here's where it gets interesting, and where most people's intuition breaks down. In quantum mechanics, we don't describe light. We don't describe any particle really as something that has a definite trajectory through space from point A to point B. When you say light moves, you're imagining light as a little thing that exists at position 1, then position 2, then position 3, traveling along a path in space. You're imagining that if we could measure very carefully where the light is at each instant, we could trace its journey. But that's not how nature works. I developed a way of thinking about this called the path integral formulation. And people sometimes misunderstand what it means. They say, oh, Feynman says light takes all possible paths. But that's a very sloppy way of talking about it. The path integral isn't a description of what the light is actually doing. It's a mathematical tool for calculating the probability of finding light at a particular place when you look for it. Let me explain this more carefully. Imagine you have a light source and a detector, and you want to know the probability that a photon from the source will reach the detector. In classical physics, Newton's physics, light would take the most direct route. That makes sense. But in quantum physics, we can't say light takes any particular route because we haven't observed it. Light doesn't have a well-defined position between emission and detection. It doesn't have a speed at every instant. These things don't exist until we actually measure them. The way to calculate the probability involves something subtle. You set up a mathematical expression that sums over all possible trajectories the light might have taken if it were classical and moving. Paths that go way out of the way, paths that double back, paths that do all sorts of crazy things. And you assign each path a weight, not a probability, but a complex number with a magnitude and a direction. We sometimes call this direction a phase. The key insight is that these contributions from different paths add up as complex numbers, not regular numbers. They can cancel each other out. They can reinforce each other. When you add up all these contributions, paths that are far from the classical trajectory tend to have phases that point in completely different directions, so their contributions cancel out. But paths near the classical path have phases pointing in similar directions, so they add together constructively. The result is that when you calculate the probability, it looks like the light mostly acts as if it took the path Newton would have predicted. But that's just what comes out of the mathematics. It doesn't mean light actually took that path. It's a mathematical convenience, not a description of reality. You know what's fascinating? If you ask me, well, what path does the light actually take? I have to tell you honestly, the question doesn't have an answer. That's not because we don't know yet. It's not like there's a path that we just haven't measured yet. The question itself is poorly formed. The light doesn't take a path in the way you mean when you haven't observed it. Nature doesn't work that way. This is connected to something even more fundamental, which is the measurement problem. When you actually perform an experiment, When you actually measure something, you get a definite result. You detect the photon here, or you detect it there. But before the measurement, quantum mechanics doesn't assign a definite position to the photon. It assigns probabilities. And the way the math works out, the way we calculate those probabilities, involves this path integral business. Now, people often ask, well, if light doesn't move, how does it get from place to place? This is a genuinely good question because it shows you're thinking carefully. But the answer requires you to let go of a certain picture of the world. Light doesn't need to get from place to place in the way you're imagining. There's no journey to make. A photon is created in an excited atom at the source. After a certain time, it's detected by an excited electron at the detector. The whole business of what happened in between, the whole story of light traveling through space, is something we invented to help us think about it. What quantum mechanics is really good at is predicting probabilities. If I set up this experiment, what's the probability of this outcome? And it turns out that when you actually do the experiment many times and collect statistics, the probabilities predicted by quantum mechanics, using this path integral method, match what you observe incredibly accurately. We're talking about precision to 8 decimal places in some cases. So even though we can't describe exactly what's happening in the space between measurement events, our ability to predict the statistics is perfect. Let me give you an example that really illustrates this. Think about a piece of glass. Light shines on it, and some reflects and some goes through. Now, why does some light reflect? You might think, well, light hits the surface and bounces. But it's not that simple. When you ask what fraction of light reflects from a particular thickness of glass, the answer is weird, and it depends on the thickness in a specific way. You can't understand this by imagining light as little particles bouncing off atoms at the surface. And you can't really understand it by imagining it as a classical wave either. The only way to understand it is through quantum mechanics. And here's the thing Feynman showed. You can calculate the amplitude for a photon to get from a source to your eye after reflecting from glass by considering all possible places on the glass where the reflection could happen. You sum up these amplitudes, taking into account how far the light has to travel along each imaginary path. Paths where the light reflects near the middle of your glass surface will have much longer distances to travel than paths near the edges. Longer path length means the phase changes more. So those contributions have phases pointing in all different directions. They cancel each other out. But there's a particular thickness of glass where something amazing happens. The path length from reflecting at the top surface and the path length from reflecting at the bottom surface happen to differ by a special amount. And that special amount is such that the phases line up perfectly. They reinforce each other. Result? More light reflects. This effect, constructive and destructive interference, is something you'd expect from waves. But here's the puzzle. If you try to measure which surface the photon really reflects from, if you put a detector there, the whole pattern goes away. Why? Because the moment you measure, you've decided it took one path or the other. You've broken the quantum superposition. The path is no longer in both places at once, in a sense. And when it's in one place, you lose the interference effect. This is the heart of what people don't understand about the path integral. The all paths language is very misleading. It's not that light actually takes all paths. It's that when you don't measure which path it takes, the mathematics requires you to consider all possibilities in a very specific way. You add up complex numbers, not regular probabilities. And the rules for adding those complex numbers are set up so that 1. Most paths cancel out. 2. You get the right probability distribution that matches experiments. 3. If you do measure something about the photon's path, the mathematics changes. You have to include your measurement information, and you get different probabilities. Think about what this really means. In classical mechanics, a particle has a position and a velocity at every instant. In quantum mechanics, neither of those things exists until you measure. The particle isn't hiding a position from us. It isn't secretly following a path that we just can't see. The properties simply don't exist until the measurement happens. And the path integral is a tool for calculating what you'll find when you do measure. Now, you might say, that's insane. Things have to exist even when I'm not looking at them. And I understand why you'd say that. But here's the thing about nature. It doesn't care about what seems reasonable to us. It only cares about making correct predictions. And these ideas, strange as they are, make predictions that are right to incredible precision. One more important point. When physicists say light travels at the speed of light, that's still meaningful even if light doesn't move in the way we're discussing. We can measure it from the reference frame of stationary observers. When we set up the math correctly, we find that energy in the electromagnetic field doesn't appear at distant locations before a time consistent with the speed of light. So causality is preserved. Information doesn't travel faster than light. The observable facts are what they are. We're just being careful about what we mean by the unobservable things in between. I think a lot of confusion comes from the language we use. We say a photon travels, light moves, the particle takes a path. These are convenient shorthand expressions that work fine most of the time, but they're not literal descriptions of what's happening in quantum mechanics. In quantum mechanics, what's fundamental is the wave function. The wave function is a mathematical object that encodes probabilities. Light is a disturbance in the electromagnetic field. A photon is a quantum of that field, a certain amount of energy and momentum. But there's no little classical particle traveling through space. The path integral formulation doesn't change these facts. It's just a different mathematical way of organizing the same quantum mechanical predictions. Schrödinger's wave equation gives you the same answers. Heisenberg's matrix mechanics gives you the same answers. They're all different mathematical languages for the same thing. Feynman chose the path integral language because he found it helped his intuition about certain problems, particularly in quantum field theory. So when we say light does not move, what we really mean is light doesn't follow a classical trajectory. The history of a light particle from emission to detection is not a well-defined path through space in the way that, say, a baseball follows a well-defined path from the pitcher's hand to home plate. The baseball has a position at each instant. The photon doesn't. The baseball's path exists independent of observation. The photon's path only makes sense in the context of what we're measuring. And here's something that bothered me my whole life about physics. We've gotten so used to talking about quantum mechanics that we sometimes forget how weird this is. I gave countless lectures about these ideas, and at the end of the day, I had to be honest with students. I don't understand it. I don't understand what light really is. I understand how to calculate things. I understand what experiments will show. But the what it really is part? That's not a scientific question. That's a metaphysical question. And science doesn't answer metaphysical questions. Science answers the question, what will happen if I do this experiment? So I'm going to end with this. We have the most accurate, most predictive physical theory ever developed. Quantum electrodynamics, the theory of light and matter, predicts experimental outcomes to an accuracy that I can only describe as miraculous. But it does this by being very careful about what it claims to describe. It claims to describe what you'll measure. It does not claim to describe what's really happening when you're not measuring. When people ask, well, if you can't see it, how do you know it exists? I say, that's the wrong question. The right question is, what will I see if I do this experiment? And we know the answer to that question. We know it with tremendous precision. What we don't know, what might be impossible to know, is what's happening in quantum systems when we're not observing them. And maybe that's okay. Maybe that's just how the universe is. Light does not move. It doesn't take a path. These are statements about what's true in quantum mechanics. They follow from the mathematics and match what we observe. But they're not intuitive because nothing you've experienced directly has ever behaved like a photon. You've only ever seen objects that persist through time, that have definite positions, that follow trajectories. Light isn't like that. Thank you for following along with this unusual way of thinking about one of nature's most fundamental phenomena. Physics isn't always obvious, but if you stick with it, if you're willing to let go of intuitions based on everyday experience, you start to see how truly remarkable the universe is. Share.